Hello everyone. In the today's session, we are discussing stress analysis of varying cross section with a different material and a different load application. You can see in the figure this component having a different cross section and with a different material and also with different loading condition. Here both the ends are fixed. The load is applied at the middle of the component. You can see it is having a different material. One component is having aluminium, another component is steel with a varying area also different, the material is also different, and the loading condition is also different. Since it is fixed at both the ends, so deformation at this portion is 0. The deformation will happen at the center, node 2 here. So whatever according to this load direction, so tensile stress will be acting in the aluminium portion, whereas the steel portion we are having compressive strength. So whatever the delta L, that is the deformation happens in the aluminium portion, is equal to the deformation happening in the steel portion. Nothing but the sign only changes. The positive displacement takes place in the aluminium, whereas negative displacement, that is compression, will take place in the steel portion. So using this equation, we have to calculate the reaction forces acting at the ends. We don't know the reaction forces, so the equation will be like the displacement of aluminium is equal to the displacement of the steel, since it is both the nodes are shared by aluminium and steel. So the positive displacement of aluminium is equal to the negative displacement of the steel. So for that, we'll go to the theoretical solution. Before going to start the theoretical solution, the given data is like Young's modulus for this aluminium portion is 70 into 10 raised 3, and the Young's modulus for steel portion is 200 into 10 raised 3. Area is 2400 for aluminium and 600 millimeter square for steel portion. Poisson's ratio remains 0.3. Let's move to the theoretical solution. So the line diagram for this component will become like this. Since the load is applying in this direction, since both the ends are fixed, so when the load is applied at this end, because this end is fixed, the reaction forces takes place, try to pull the this aluminium portion, whereas the steel portion, the reaction forces try to push the steel portion opposite to the load direction, since it is fixed here. So the equation for this component will be like RA, the displacement of the portion 1 is equal to the displacement of the portion 2. We have to substitute the values here. So we know that for delta L, the formula is PL over AE. Instead of P, we are substituting reaction loaded, because we don't know what are the reaction shared by this node 1 and node 2. Since load is applying at the middle, this whatever the load is applied at the center is shared by these two reactions. So these reaction loads we need to calculate. So for calculating that, we are taking this equation as delta 1 equals to delta 2, that is displacement of the aluminium portion is equal to the displacement of the steel portion. So we substitute the values RA by L into L1 divided by A1 into E, RB into L2 divided by A2 into E. Before that, the equation will form like this. The total load is acting on this component is 200 into 10 raised 3 Newton. So this load is 200 into 10 raised 3 Newton. So whatever load is acting on this component is shared by these two reactions. So RA plus RB, if you add these two reactions, the total load will be 200 into 10 raised 3. We have to assume that this as a equation 1. So using this equation, so we have to calculate the RA and RB. So if you simplify, substitute all the values given here, only left thing is RA and RB, we don't know that. By simplifying this equation, we will get RA equals to 1.86 times the RB. So we know that RA plus RB equals to 200 into 10 raised 3. Substitute the RA value here. So if you substitute that, we'll get RB as 69711.62 Newton, or 69.77 into 10 raised 3 Newton. So we know that Ra plus Rb equals to 200 kilonewton. So if you minus this with the Rb value, we'll get Ra as 130.24 into 10 raised 3 Newton and Rb is 69.77 10 into 10 raised 3 Newton. So we got the Ra and Rb values, this one and this one. Ra we got as 130 whereas Rb approximately 69 kilonewton. So next move to the deformation. We know that this component is fixed at both the ends, this end and this end. So at node 1 and node 3, the deformation is 0. Only the deformation happens at node 2, that is same for aluminum and steel. So you can substitute any values either of aluminum or either of steel. We'll get same value. Only thing is that in aluminum we'll get tensile elongation, whereas in steel component we'll get negative, that is compressive elongation. So substitute any one value, we'll get same answer. So we are substituting the value of aluminum here. So Ra, P with nothing but Ra. So Ra is 130.23 into 10 raised 3, L is 300, area is 2400 into Young's modulus of aluminum is 70 into 10 raised 3. We'll get deformation at node 3 as positive 0.2325 Newton. You can substitute the values of steel also, we'll get same value. Only thing is that we'll get negative value here, minus 2325, because the compression will happen in the steel portion. Next, you have to calculate the stress. We have two elements here. For element 1, stress will be Ra by area 1. Ra we got it as 130.23 into 10 raised 3. We are converting this kilonewton into Newton. So we are adding 10 raised 3. Area is 2400. So the stress will be 54.26 Newton per millimeter at element 1. Similarly, at element 2, Rb by A2. Rb we got it as 69.77 into 10 raised 3 divided by area 2 is 600. So if you substitute, you will get the stress at node element 2 as 116.28. So reaction we already calculated. Ra is 130.23 and Rb is 69.76. Both are negative direction. Now let's move to the Ansys and we'll model this component and try to find the solution and to compare the values there. So go to the Ansys software. Go to Preferences, Structural, OK. Go to preprocessor, element type, add, edit, delete, add, link 3D finite STN 180, OK. Close this. Then go to real constant, add, edit, delete, go to add, click here, OK. So area of first component is 2400. Click on OK. Now go to add, OK. So set number 2, the area 2 is 600 millimeter square. Click on OK. So we got two sets here. One is 2400 area, another one is 600 area. So close this. Now go to the material properties, material models, that go to structural, linear, elastic, isotropic. Now you have to enter the Young's modulus of the first component, that is steel, 73 is given. Okay. Young's modulus Poisson's ratio is 0.3. Click on OK. Now you have to enter the another material. So you have to go for material new model. Click ID 2. OK. Linear, elastic, isotropic. Click on this. Now the Young's modulus is 203. Poisson's ratio is 0.3. Click on OK. Close this. Once you check the values, whatever entered is correct. So the Young's modulus is 70 into 10 raised 3 for aluminum and steel is 200 into 10 raised 3. Now once move to the modeling, create key points in active CS, mode number 1, Click on apply. It will take first node in origin and second key point. Enter the value. Length is 300. Length. The length is 300. Click on apply. Now third key point, it's 700 length. 300 plus 400. Click on OK. Three nodes key points are created. Using these three key points, create a line. Go to lines, straight line. Select the first and second key points. Click on OK. Again, go to straight line. Click on 2 to 3. Click on OK. Now the model is created. Now go to the meshing. Click on mesh attributes. Click on picked lines. Select the first line. Click on OK. Everything should be in first set, so that it will be first set. We have given the everything related to aluminum part, so everything you have to give for first portion here. Real constant number, set number, material number, everything. Click on OK. Now again click on second, click on picked lines, select the second line, click on OK. Now change the everything to set number 2, second here, second here. This will remain same. Click on OK. Now the metal properties has applied this as we have applied this line as aluminum and this line as steel. Now move to the size control, manual size, global size. Here you 10 is length and division should be 100. You can give any length. If you increase this, the result will be very accurate. Click OK. Then go to mesh tool. Click on mesh. Select pick all. Now the meshing portion is over now. Go to applying the load. For that we are going to solution, define load, apply, structural, displacement on key points. Select this node and this node. Both nodes are fixed. Click on OK. Select all DOF. OK. Both the ends are fixed now. Now go to force movement on key points. Now select the center key point here. Click on OK. Give the load in Fx direction, that is 200 kilonewton. So 200 into 10 raised 3. I'll give OK. Load of 200 kilonewton is applied at the key point 2. Now go to solve, current ls. OK. Solution is done. Close this. Now go to general post processor. That go to element table. Go to define table. Add by sequence number ls, 1. Click on OK. Close this. Now the solution is left. Go to plot result, deformed shape, deformed plus undeformed. Okay. You can see the maximum deformation is 2.232528, which is exactly same as our theoretical calculation. Then go to contour plot, element table. Okay. You can see the stress value here 54.26 and 116.26, which is maximum here and minimum here. So next go to line element result, click on OK. You can see the stress values. One side is positive, one side is negative. You can see that. Now go to least result, nodal solution. In that nodal solution, DOF of solution, displacement vector sum. Okay, so this is the maximum displacement 0.23258. Then go to least result, go to reaction solution. Here you can get reaction load. You can see that 1.130 into 10 raised 6, that is nothing but 130.23 and 69.666767, which is exactly same as theoretical calculation. So next you got to see the nodal solution. Go to DOF of solution, X displacement vector. Okay, you can see the displacement. Maximum displacement is 0.2356, which is same as our theoretical calculation. Next you go to element table data to see the stress less. Okay, you can see the stress here in each division. Since we have made number of division, so in each division you can see the stresses, which is 54.26 and 116.28 is the two maximum values. You can see here. So all the values are matching with the theoretical calculation. So that's it for the today's session. Thank you.